This is section 4.5. Everyone's favorite topic, application problems. We're going to the word problems. These are going to be specifically word problems or application problems involving exponential functions. And in the process of solving for some of these problems, we're going to use logarithms as well. So it just gets better and better. The two types of applications we're going to look at in this section, financial applications and some natural occurring phenomenon. So financial investments, we're going to look at compound interest. And then we're going to look at some naturally occurring phenomenon where things grow or decay at an exponential rate. So let's start with the financial part, compound interest. And as you're viewing this video, it would be wise to pause every now and again to make sure you can write down formulas and what all of the variables mean in each formula. So for compound interest, we're going to use this formula right here. Now, I would not worry about memorizing this particular compound interest formula. If this formula is needed on an exam, it will be embedded in the problem to solve, so you don't need to worry about memorizing this. Now, how compound interest differs from, say, simple interest. An example of simple interest involving financial investments. If someone were to invest $10,000 into an account, and at the end of the investment period, their growth would be 10%. That's simple interest. Regardless of how long it's in there, at the end of the investment period, they're just going to get 10% of the original investment one time. That's it. That's simple interest. Compound interest differs in that interest is accrued at regular intervals. So, for example, if you deposit money into an account that compounds interest every year, let's use $1,000 as a simple example. If you invest $1,000 into an account and the interest is going to compound every year at, let's say, 10% to keep things simple. So at the end of year one, you're going to get 10% of 1,000, which is $100. So now your new balance is $1,100. At the end of year two, however, you're going to get 10% of not the original investment, 1,000, but you're going to get 10% of the new balance, which is $1,100. So 10% of that is $110. So now your interest has grown. So now you had $1,100. You add another $110. Now you have $1,210. So at the end of year three, you're going to have 10% interest on $1,210. So the interest that accrues at the end of each period is determined by the growing balance of the original investment. That's called compound interest. Now, compound interest could also be, instead of compounded every year, it could be twice a year, 4 times a year. So that's what these variables are. A of t is just the future amount after some period of t in years. P is the principal investment. That's the amount that's initially deposited into an account. R is the interest rate. The most common mistake I see students use with R is, remember, a percent is not a number that can be used in a formula. So if the interest rate is 4%, you need to change the percent into a decimal, 0.04. That's probably the most common mistake I see. N is the number of times per year the interest is going to be compounded. So in the previous example, if it's compounded annually or one time a year, then n would equal 1. If it's compounded semi-annually, then that's twice a year, so n would be 2. If it's compounded quarterly, that means 4 times a year, so n equals 4, and so on. And t is time in years. So an example here of compound interest. So take a moment, pause it, write this problem down. Now, $10,000 is initially deposited or invested into an account yielding 4% interest compounded semi-annually. How much money is going to be in this account after 15 years? So we need to use this formula and decide what the value of each of those variables are. Now, part of the issue of solving a word problem is figuring out what the problem is asking so you know which variable to solve for. The question is, how much money will there be in this account? That's a future amount. So we're solving for A, the future amount, which means we need to plug values in for P, the principal investment, the interest rate, the number of times it's compounding, and the number of years. So we need to have values for all of these variables so that we can solve for the future amount. So the P, the principal investment, is $10,000. The interest rate is 4%. But remember, 4% is not a number that can be used in a formula. It's 0.04. The interest is compounded semi-annually, which means twice a year. So n is equal to 2. And then the amount of time that this money's going to be in this account, or at least we're going to check after so many years, is 15. We're going to see how much money is in this account after 15 years. So the amount we're looking for is after 15 years. So the amount after 15 years is equal to $10,000. The interest rate is 0.04. The number of times it's going to be compounded per year is twice. And then the exponent is the number of times it compounds multiplied by a year. So this is 2 times 15. Now definitely at this point, this becomes a calculator problem. This is not something that's going to be calculated by hand. What I'd recommend is you, unless you're very, very confident with using parentheses and exponents on your scientific calculator, I'd recommend you break this down into a couple of chunks. Figure out what this base is first. 1 plus 0.04 divided by 2. That's a number that's just slightly bigger than 1, like 1.1, maybe something like that. Okay, so take that base, raise it to the 30th power, and then multiply that by 10,000. Or, like I said, if you're pretty confident with using your calculator, you may be able to just plug this whole thing in at once and hit enter. Bottom line is we just need to plug this into a calculator, figure out how much money remains. After 15 years, $10,000 has grown to what amount? That's what we're trying to figure out here. Let's go ahead and pause it for a minute. Plug that into your calculator and see what value you get. I'm getting $18,113.62. So the $10,000 initial investment has grown to $18,113.62. So the interest earned after 15 years was $8,113. Now this is assuming that after the initial deposit, the money was just left alone in the account. There were no future deposits or investments other than the interest that's growing. So the only thing that you can expect to be different on a problem like this is just changing either the interest rate, the principal investment, or how often it's compounded. So part B here, what if the interest is compounded quarterly? So let's use the same example as above as far as interest rate and principal investment. And number of years is going to be 15 years still. But what would change if the interest is compounded quarterly? So for here we would use n is equal to 4. Quarterly means 4 times a year. So the amount after 15 years is going to be the same principal investment, $10,000, and same interest rate, 4%. Now we're going to divide this by 4. It's going to be raised to 4 times 15. So if it's compounded more often, instead of twice a year, the interest is going to accrue and be evaluated every 4 times a year. So this is going to affect the growth of the money. It's going to grow quicker. The question is how much? Is it going to be significantly more? Just slightly more? So pause it here, run this through your calculator, see what you can get. I'm getting $1,66.97. So if it's compounded twice a year, semi-annually, is $18,113. Four times a year, it's $18,166. So it wasn't a significant change in the growth. It did grow a little quicker. It was the same amount of time, still 15 years. Let's see the effect of if the interest is compounded monthly. So for this one, if it's monthly, then the number of compounding times in a year is going to be 12 for 12 months in a year. So now the amount after 15 years is $10,000. We still have the same interest rate of 4%. Now it's going to be compounded 12 times a year. And the exponent is going to be the 12 times a year times the 15 years that it's in the account. So what's the growth going to be? What's the $10,000 going to grow into after 15 years? I'm getting $18,000, well, $18,203.02. So the point here I'm trying to illustrate is the number of times it compounds in a year really doesn't affect the growth rate as much as you would think. What does is obviously interest rate. The biggest contributing factor is time. The longer you leave the money in an account that's growing exponentially, obviously you're going to get better growth the longer you leave it in there. So it's not the number of compounding cycles. It's either a higher interest rate or just leave it in the account. Now, after a while, if you keep changing the number of compounding times in a year from, let's say, monthly to every week or to every day, or if it's compounding every 10 seconds, eventually n is going to be quite large. So I did not introduce this back in section 4.2, but I want to talk briefly about the number e that we used as the natural number. The approximate value is 2.71. This part here you do not necessarily need to take notes on unless you want to. This is just a little background on the number e and how we get this value of 2.71. So this ratio right here, 1 over m, 1 plus 1 over m to the power of m, this is an exponential expression. And this table here illustrates as you increase m from 1 to 10,000 to 1,000,000, as m increases, what happens to the value of this overall expression? So if you plug a 1 in for m, you're going to get 1 plus 1 over 1, which is 2, raised to the first power, which is 2. If m changes to 100, this grows to 2.7048. If it's 10,000, so you can see that as m continues to increase, this value here starts to grow a little more slowly, 2.71814 to 2.71828. As you continue to increase to 1 billion to 10 trillion, it's going to be 2.71, and then just going to have changing decimals way far down the road here. So what we say is as m approaches infinity, so as m gets sufficiently large towards infinity, this value here, this expression, 2.71, is the value of e. It's a irrational number, meaning the decimal never stops and it never has a repeating pattern, kind of like pi. What does all this have to do with compound interest? Well, the compound interest formula they're going to use is this, with some slight algebraic manipulation. And again, you don't need to remember this, but just by manipulating the location of some of these variables, not changing the value of the expression, just changing the orientation of some of the variables, we end up with this. It's the same formula as this, but that I'm pointing to right here, this that I'm pointing to, 1 plus 1 over n over r to the power of n over r, is just this expression in disguise. So as n approaches infinity in this expression, then this expression is going to approach the value of e, which is 2.71. So this is going to turn into a base of e. We have the principal investment and the rate times time. So as n approaches infinity, instead of this compound interest formula that we've been using on the previous examples, we're going to use this formula here, which is called continuously compounding interest. What this means is instead of compounding every month or every day or every second, it's always compounding. It's continuously compounding. So that's a slightly different formula than just the normal compounding interest formula. So P is the principal investment. E is just the natural number E, 2.71 approximately. R is interest rate, T is time. So if in the example or homework problems you're trying to solve, it's stated that the interest compounds continuously, this is the formula that you're going to use right here. So in this example, go ahead and pause it, write this example down. We're going to use the same numbers as the previous example, $10,000. It's invested into an account with 4% interest, but now it's compounded continuously. So we're going to check to see how much is in this account after 15 years. So the amount after 15 years, we're using this formula here, PERT for short, so principal investment multiplied by the base E raised to the rate times time. So the amount after 15 years is equal to the principal investment, $10,000. Our base is E. The exponent is the interest rate, 0.04, times the number of years, which is 15 years. And again, calculator problem. All scientific calculators have a base E button on there somewhere. So take a moment here, pause it, find all the buttons you need on your calculator, but plug this in, and let's see what happens to this investment of $10,000. Now, in the previous 3 examples, it was compounded semi-annually, quarterly, and then monthly. It was still right around $18,100. Is this going to significantly change if it's now compounded continuously? And the answer is not really. So the amount I'm getting after 15 years of continuously compounding interest is $18,221.19. So these are the type of problems you'll see in the homework involving compound interest or continuously compound interest. Now again, if it's compound interest, where it's compounding at regular intervals, you don't need to worry about memorizing that formula. The continuously compound interest formula is typically expected to be memorized. So this amount equals P times E to the rate times time. That is most likely something you'll need to remember. Now, the last part of this this section involves it's still exponential type situations. It's growth or decay problems. We're actually going to use pretty much the same formula as continuously compounding. So this formula here is continuously compounding. When we're talking about naturally occurring phenomenon that grow or decay according to an exponential model, we just changed the definition of some of the variables is all. So instead of a principal investment for a financial situation, A sub 0 or A naught is the initial amount. A of t is still the future amount at some time t, but this subscript of 0, A sub 0 or A naught is just the initial amount present. E is the base E, it's the natural number, 2.71 approximately. Instead of an interest rate for a financial situation, we have K, which is called a relative growth or decay rate. So if the value of K is bigger than 0, it represents a growth problem. If the value of K is less than 0, it represents a substance that's decaying exponentially, like radioactive isotopes, things like that. And again, T is time. So an example here, you can pause it and write this example down. So we have some kind of lab technician observing in a petri dish a colony of bacteria has 10,000 cells. That would really suck to be the person that had to count all those. But this technician observes that after 3 days, that 10,000 cells has grown to 500,000. So we're going to assume that these cells are growing exponentially find a formula for the number of cells in thousands after t days. So this phrase here, assuming that this grows exponentially, that means we're going to be able to use this exponential growth model right here. So we need to define or find variables because the question is find a formula for the number of cells in thousands. So let's pick out what we know. We know that E sub 0, the initial amount. Now we've got to be very careful, and I almost forgot, but it says find a formula for the number of cells in thousands. And they'll often throw this into formulas where the numbers are a little bit larger, like 500,000, 10,000, or a million. So in thousands, the colony of bacteria starts with. So if it's 10,000s, then in thousands, the number is going to be 10. So the initial amount we're going to use for the formula is 10 because in thousands, this becomes 10,000. And along that same line, then the future amount, A sub 3 after 3 days, is 500,000. So in thousands, 500,000 becomes 500. So this is 500. And time is 3 days. So our formula becomes, if we're going to use the relative exponential growth, it's A of t, A naught, e to the kt. This becomes 500. Remember, though, it's 500 in thousands, so it's 500,000 equals 10 e. We don't know k, and t is going to be 3 days. So we need to find the value of k in order to have a formula. So the formula is going to eventually be something like A of t equals 10e to the whatever the value of k is times 3. That's going to be the formula that we end up with. So what we're doing now is just finding the relative growth rate because that's missing in our given information. So the relative growth rate k, the variable we're solving for, is in an exponent. We've talked about this a number of times up to this point. You cannot solve for a variable if it's in an exponent unless we can somehow cancel the base so that this is no longer an exponent. Sound familiar? What cancels a base, particularly what cancels a base e, is natural log. So we got to get this term by itself, the e and the k to the k times 3. So we're going to divide by 10. So that becomes 50 equals e to the k times 3. Now we can use natural log on both sides because remember natural log cancels base e. So now we have the natural log of 50 is equal to k times 3. To get k out by itself now, we simply divide by 3 on both sides. So the exact value of k is equal to the natural log of 50 divided by 3. That's going to be kind of awkward to use in a formula, so let's get the approximate value. Again, this calculator problem. So pause it here, you type this into your calculator. So that's roughly 1.3. So now we can complete the formula. So this formula would be the amount at any time t is equal to 10, representing the 10,000 initial bacteria cells, e, and then in place of k, we're going to put the approximate value 1.3 times t. So what we could now use this formula for is to estimate the number of bacteria cells at any given time t. So we could say after 10 days or 2 weeks or 5 years. Now remember, whatever you plug in for t, since this value here, 1.3, was calculated using days, 3 days, the value for time has to match that. So if it's 2 weeks, you wouldn't plug in 2 for t, you would plug in 14 because it's 14 days. That's just something to keep in mind. Your units of measure need to match. So that's what they're talking about when they're saying find a formula or find an equation or a function if it's involving exponential growth or decay formula, it usually involves finding the relative growth rate first, and then finding a general formula for any future amount at any given time t, according to that relative growth rate. Now, just a further example, this would be an example of exponential decay, and it typically involves some kind of radioactive isotope or some kind of isotope that decays exponentially. This is iodine 131. It's used in some medical procedures, but it has a half-life of approximately 8 days. So if 5 grams are present, we need to again find a formula that gives the amount in grams after t days. So let's write what we know. If we're going to use the relative growth rate exponential function, then that's again a of t is equal to a naught or a sub 0 times e to the kt. So the initial value is, in this case, 5 grams. Now they kind of imply in the problem the future, some kind of future amount. It says that the half-life is 8 days. So in order to find k, we need to have values for all of the other variables. So we need to have t and we need to have a future amount. So if we just use the half-life, that after 8 days, half of the amount is remaining. So we could use the half-life of, if t equals 8, then the amount after 8 days is 2.5 grams. That's the half-life. So we could use now 2.5 for a of t is equal to the initial amount, 5, times the base e. We don't know the relative growth decay rate, but the amount would be 8 days in order to be a full half-life. So every variable has been filled in except for k, the relative decay rate. So we solve this one exactly like we did the last example. K as a variable is in an exponent, can't be solved unless we can cancel the base using a natural log. So we're going to divide by 5 on both sides. So that's just 1/2 e to the k times 8. So natural log to cancel the base e. So the natural log of 1/2 now is equal to k times 8. So we can divide by 8 to get k by itself, the relative decay rate. K is the natural log of 1/2 divided by 8, which is approximately negative 0.0866. For these relative growth or decay rates, it's wise to use as many decimals as possible just to be more accurate. If you're going to use it as a model to make predictions in medical procedures and things like that, accuracy is important. So I tend to use a few more decimals for these relative growth or decay rates. So that's the value of k. So now we can finish the decay model would be the amount at any time t is equal to the initial 5 grams times e. The exponent is our decay rate here, negative 0.08664 times t. So again, what we could use this for, this model, is estimating the amount remaining of the 5 grams, the amount remaining at any given time t. So we know after 8 days half the amount, but how much would be left after 30 days or 4 months or a year? So that's what this model could be used for. So as far as your homework or test preparation goes, for this section, 4.5, you need to be familiar with exponential problems involving compound interest. So we had compound interest formula here, in which the interest compounds at regular intervals per year n. We had the continuously compounding interest formula, A equals principal times e to the rate times time. And then we had our growth and decay problems that essentially use the same formula as continuously compounding interest here. And those as the two examples we just did show, typically you start by finding that relative growth or decay rate first, and then writing the model that could be used to make future predictions.